Good morning. How are you?
Miss Denny?
Yes, sir.
We get the Q2?
You have Q2.
Oh, we have.
Yep. You should have had, I gave you Q1, Q2 together at the beginning of the year. So you've got Q2. There should be a little divider right in between.
Yep.
There it is. It is. It's crazy, right?
It's cold.
I love it.
That may mean it will snow if it's getting this cold. This hot.
Maybe we'll get lucky. Well, depends on if you like snow. Do you like snow?
I really wish it's one time
I do.
on my birthday.
I like
Danny,
snow. Yeah.
it's never been a snow in Georgia so far.
Not since you've been here. We've had them. We had some good ones in the past, but
Snow. I've never had like real snow.
a good snow,
Yeah,
a real good snow.
Snow.
When's your birthday, Lucy?
December 8th. Birthday, it snowed really good. My dad even made
Fourth
snow.
birthday.
Well, I don't know if it's gonna snow on midterm. Let's.
Well, if it snows on midterm, your parents will be proctoring them at home. That'll be fun.
Do we have to answer the questions?
That is your midterm review, so you don't have to turn it in. But if you do all that, if you answer all those, you'll be all set for the midterm. You'll have everything you need. Let's talk about what is going to be on the quiz. What's going to be on the quiz? What do you think? Verb. What kind of verb? A are verb. So I would say these meanings. So what'd you do this weekend, Miss Lucy? Anything fun? You didn't get to be home. Why not?
Mom's sick.
Oh, is your mom gonna be okay?
My dad's
Um,
last Tuesday.
stuck with your dad? And your mom's just sick in general, not well. Oh, gross. Yep, that means you have it.
She doesn't have COVID. So she's negative.
Okay, good.
She's just sick. Hope it's not the flu.
Yeah, really.
Flu is bad.
Exactly. And if I wanted to say, what would be what would be the yoga ending? Hopefully she can get better soon. That's no fun. Being sick is no fun.
There's last Tuesday.
Yeah, yuck. No good. No good.
Week.
He's good, thank you. He's just chilling right now in his room. He loves it in his room. He feels safe in there, so he's just sleeping. He likes the cooler weather. He was running around out there this morning in the grass, and the grass is all wet, right? Cause it's all dewy out there, so he comes running upstairs while I'm getting dressed, he comes running upstairs to my bedroom. His routine is to get on my bed while I'm getting dressed. He likes to sit up on my bed, but he can't get there on his own. I have to lift him up because my bed's very high and he's very short. So he comes running in soaking wet and then stands at the base of the bed with his tail wagging, looking at it like, come on, you know, you want to pick me up and put me here. And I'm like, dude, you are wet. So I had to get a towel and dry him off before. What have you got there?
This is a little bear that my dad gave me.
Oh, he's cute.
It's a little drum bear.
A little drum bear. I like that. With your dad being the drummer. That's great.
It was given to him in high school. And I found it in our playroom at my grandparents.
Oh, okay. That's even cooler. Does he have a name?
No.
No.
I don't know what the name.
Ooh, I have a suggestion. Paradiddle.
That's what my dad's last dog was named.
Ah, of course it was.
Diddle.
It's a drumming thing. Paradiddle's a drum thing, so I.
Diddles with the drums because she diddled all over the floor. And she was a small, so small.
You could call him Tom, like a tom. Actually, I had a friend in high school who had an iguana, and he named the iguana Zildjian. That's a brand of cymbal.
A real one?
Yeah, a real one.
Is it a toy?
No, real one. A pet. But his name was Zildjian, because that's a brand of cymbal.
I think naming him Sticks.
Sticks is a great name too for a drummer bear, right?
Even though he doesn't have any drumsticks. He just has a little paw.
It's all good. He lost his sticks. That's his problem. What you reading now?
It's the complete high school study for chemistry.
Okay. She's prepared over here. I expected something like, oh, it's about dragons or whatever, but no. She's going complete high school study for chemistry. All right. Do you like coding? We got a couple coding books, but nobody really got into it around here.
My brother's coding book. I have history, which I love.
I love history too.
I saw your Halloween decorations, including the skeleton dots, and
Kind of hard to miss, isn't it? I got it everywhere. Yep. Thank you, ma'am. Yeah. So that is your midterm review that you're collecting. So you're gonna want to clip it in your binder where it's safe. That will be for you to study. You're not going to turn it in, of course. You're not going to turn it in, but you're going to use it to study for your midterm. And it's got a bunch of blanks in it. And if you fill them all out, you'll be set. You'll be good to go. And I will be putting out for you you'll be able to access a blank copy online and a completed copy online. Yes, ma'am. What you got? We are on unit 4. Yep.
I mean 5, I think.
The unit 4 is elements and the periodic table.
Yeah, it's just set up differently.
This is
It's
Danny.
okay.
I can't find a pencil.
You can't find it here?
No. Is that a pencil?
It's an empty pencil.
No.
Oh, this one's good. It's got a little extra lead there. Okay. So you got your midterm study guide. Study that, and you'll be good for your midterms. All right, everybody get out today's stuff. Oh yeah, Annabelle, I gave you lab 7 back because I didn't need it. I'm not sure if you turned it in by accident or what, but I gave it back to you because I don't need it. I'll give you a second to get yourselves organized since I just handed out stuff. It sure looks like it's gonna rain, but it's not. It's very gray and breezy. I had the windows open and the doors open yesterday. It was beautiful.
Yeah, it's really starting to feel like fall, especially with the cold front.
Yeah, it really is. Yeah. I know they're starting to go just a little bit. I love to go up to the mountains when all the leaves turn.
Can I spell binary? Like
B-I-N-A.
Hey,
Mm-hmm.
binary.
Yep. R-Y. All right, are we ready, people? This is lesson 9, which makes it the last lesson of the first quarter, which means that after you finish your test and I get all of your grades in for this quarter, you'll get your first progress report.
Hey,
Mm-hmm.
and will captains change?
Yes, next week you will have new teams, new captains. Everything will be new. You'll be scrambled up. You gotta be a senior rat to be a captain, but you have a different captain. You have to be what? You have to be returning first quarter. After that, you can be new. But first quarter is returning. All right. So we are wrapping up Q1 today, people. So I want to start with this great little TEDx on how atoms bond. And we'll probably get a commercial, so I apologize before it starts because I can't seem to make them stop. Oh no.
Wait, that's
Hang on, it's already started. Let me back it up. How'd that happen? Yeah. Where did it go?
Excuse me?
That's bizarre. It just switched over entirely. Okay, hold on. Alexa, turn on Media Center. It just swapped over entirely what it was supposed to be on. I don't know why it did that, but it did. There we go. All right. You have what you need, Lucy?
Yes, I just need to grab it.
We're kind of low.
Hey,
Make sure it works.
Who's that person
I
who
have-
figured out
Who what?
Earth was round?
Are you talking about like Galileo or something
Oh,
about
yeah.
the Earth being at the center? Okay, here we go. I mean, Earth not being.
Most atoms don't ride solo. Instead, they bond with other atoms. Now, bonds can form between atoms of the same element or atoms of different elements. You've probably imagined bonding as a tug of war. If one atom is really strong, it can pull one or more electrons off another atom. Then you end up with one negatively charged ion and one positively charged ion. And the attraction between these opposite charges is called an ionic bond. This is the kind of sharing where you just give away your toy to someone else and then never get it back. Table salt, sodium chloride, is held together by ionic bonds. Every atom of sodium gives up one electron to every atom of chlorine. Ions are formed, and those ions arrange themselves in a 3D grid called a lattice, in which every sodium ion is bonded to 6 chloride ions, and every chloride ion is bonded to 6 sodium ions. The chlorine atoms never give the sodium atoms their electrons back. Now, these transactions aren't always so cut and dry. If one atom doesn't completely overwhelm the other, they can actually share each other's electrons. This is like a potluck, where you and a friend each bring a dish, and then both of you share both dishes. Each atom is attracted to the shared electrons in between them, and this attraction is called a covalent bond. The proteins and DNA in our bodies, for example, are held together largely by these covalent bonds. Some atoms can covalently bond with just one other atom, others with many more. The number of other atoms one atom can bond with depends on how its electrons are arranged. So, how are electrons arranged? Every atom of a pure, unbonded element is electrically neutral because it contains the same number of protons in the nucleus as it does electrons around the nucleus. And not all of those electrons are available for bonding. Only the outermost electrons, the ones in orbitals furthest from the nucleus, the ones with the most energy, only those participate in bonding. By the way, this applies to ionic bonding too. Remember sodium chloride? Well, the electron that sodium loses is the one furthest from its nucleus. And the orbital that electron occupies when it goes over to chlorine is also the one furthest from its nucleus. But back to covalent bonding. Carbon has 4 electrons that are free to bond. Nitrogen has 3, oxygen 2. So carbon is likely to form 4 bonds, nitrogen 3 and oxygen 2. Hydrogen only has 1 electron, so it can only form 1 bond. In some special cases, atoms can form more bonds than you'd expect, but they better have a really good reason to do so, or things tend to fly apart. Groups of atoms that share electrons covalently with each other are called molecules. They can be small. For example, every molecule of oxygen gas is made up of just 2 oxygen atoms bonded to each other. Or they can be really, really big. Human chromosome 13 is just 2 molecules, but each one has over 37 billion atoms. And this neighborhood, this city of atoms, is held together by the humble chemical bond.
Okay, so keep that in mind. We just mentioned 2 different types of bonds. What 2 types of bonds did we mention in that video? All right, Miss Annabelle.
Chemical bond.
They're all chemical bonds, but 2 types of chemical bonds. Everly. Ionic is one. What's the other? Covalent. Okay, ionic and covalent. In an ionic bond, it said it's like you bring your friend over to your toy over to your friend's house and your friend takes it and never gives it back, right? So it's basically one donates and the other steals, right? And then covalent, they share. It's like a potluck. Okay.
I think I did that once when I was like 5 or something to my friend. I kind of stole their Legos.
Yeah, that happens.
Ionic bond happens when when one element takes an electron from a valence electron and keeps it with this.
Yes, it keeps it. Yeah, in an ionic bond. Yeah, the one that's stealing, remember we talked about it last week, it keeps it. They don't share. So I made this slide directly from your workbook, right? So it says here, why is it important that the billions of spatulae coming into contact with the surface of the gecko, why is it important that, billions of spatulae come into contact with the surface when the gecko is climbing? So this talked about the gecko. So it says, have you ever seen a gecko climbing up a wall or running across a ceiling? Geckos seem to defy gravity. They have tiny hairs that cover the pads of their feet. These hairs branch out into hundreds of smaller structures called spatulae. When a gecko climbs a wall, billions of spatulae on its feet come into contact with the surface. Scientists believe that geckos can stick to surfaces because of the billions of small attractive forces called van der Waals forces between the molecules of the spatulae and the molecules on the surface. Now that scientists are developing adhesives that can copy the characteristics of the spatulae. So, are y'all lost? Oh, did we find it? Okay. So, anyway, why do you think it's important that billions of these spatulae come into contact with the surface when a gecko is climbing? Why do you think?
So that it can get a firm grip.
Yeah, so that it gets a firm grip. So if you ever look, you can look at gecko feet under a microscope. They've done them with microscopes and gotten like electron microscope, got really good pictures. They have tiny little like hairy like things that they're so small that there is molecular attraction between them and whatever the surface is. And that's what helps them stick to stuff. You ever watch them? They can walk up glass, they can walk across ceilings.
We're gonna do that in biology?
No, we'll I think there may be a picture of it in one of your biology books, but we're not gonna like do it in a lab. I don't want to cut their little feet off. So yeah, so basically more spatulae in contact with the surface means more attractive forces between the gecko's feet and the surface. All right, so what we're talking about now is attractive forces between substances, between particles, between molecules. So what uses do you think you could find for an adhesive that works like a gecko's foot? What do you think? Does anybody have any ideas? What do you think?
Suction cups?
Yeah, that's a great example. Yep. What else? Anybody else have any other ideas? No? So they do make tape like this now. And they also make there are some silicone that uses similar structure, similar adhesive. And Annabelle, pay attention to today's lesson. Do that when you get home so that you don't want to miss what's going on today. So anyway, they're really good for helping things stick, and they make like silicone that you can attach to your body actually, and then just peel it right off. For example, they make a silicone that you put on wounds, okay? And it comes on a little pad and it's stretchy. And like, so I had my appendix taken out about 6 years ago. And they, they had to put little glue and stuff where they do it with probes, right? They go and they punch 3 holes in you. They don't have to cut you open. Just punch 3 holes, but they leave little scars. So if you take the silicone that's the medical grade stuff, it sticks to you, but there's no glue. There's no like adhesive glue. It's actually just the structure of the silicone. And it's kind of mimics the way gecko's feet work. It's really cool. And because of that, it keeps pressure and moisture on a healing wound, and it reduces scarring. Like you can barely even see my scars because I use that stuff. It was amazing. So some examples would be bandages or even sticky notes. They would be really sticky notes. Yeah. So a chemical bond formed when 2 atoms share an electron is called a covalent bond, right? You see it right there. And the attractions between the shared electrons and the protons in the nucleus of each atom hold the atoms together in a covalent bond. And 2 bonded fluorine atoms form a molecule. So things that are covalently bonded are molecules. So a chemical bond formed when 2, I should say 2, that's spelled wrong, sorry. 2 atoms share electron is called a what kind of bond? Annabelle?
Covalent.
Covalent bond, very good. And what is a neutral group of atoms joined together by covalent bonds? No. Neutral joined by covalent bonds. What do you call that? Ionic bonds, we call it an ionic compound. But when their atoms join together covalently, we call it a molecule. This is that word molecule. And remember, a molecule can be different types of atoms bonded together or the same, like 2 oxygen atoms is an oxygen molecule. 2 hydrogen atoms is a hydrogen molecule.
Formed by the covalent bond is a molecule.
A molecule, correct. So if you're doing a metal and a non-metal, which is what we talked about last week, you get ionically bonded compounds, ionic compounds. But if you get any of these other things start mixing in, that's when you get molecules. All right, so this talks about double bonds and triple bonds, and we'll come back to that. So atoms in a covalent bond are held together by what? What do you think? Do we know? So the attractions between the shared electrons and protons in each atom's nucleus. It's the same thing that holds together ionically bonded compounds, right? It's the idea that you've got an attraction between your negative particles, your electrons, and your positive particles, your protons, and then your valence electrons, once again, are the ones that matter. They're the only ones that are going to play the game. Everybody else is tucked in tight and they're not going to play. Yes.
I have a question. So like, in quarter 2, will we have to come up with like a whole new name and like?
Yeah, new lab team. Yep. So this says wires right here. Is this little bit on headphones? Do you see it? Wires such as the ones found in your headphones, if you still have wired headphones, are insulated with plastic or rubber to prevent electric current from flowing between wires. The insulation also allows you to touch the wires without being shocked. What are some other objects that have insulated wires? Emerson. Chargers, yeah.
That's what I was about to say.
Ah,
Like the plug points, like
Lucy? Computers have wires that are insulated, yeah.
Cords.
Any kind of cords, you're
Yeah.
right. Yeah, right. So any of those things would be good answers. Coffee makers, lamps, toasters, your cell phone chargers, MP3 players if you still have those. So yeah. Why is that? Why are we doing that? Why are we doing
to prevent you from getting electric shocks, since like,
right?
Because that can
Uh-huh.
kill you.
and
So-
insulator won't cause any electric shock since it's a insulator is a poor conductor of electricity.
Right. Okay. So one of the properties of molecular compounds is that they have poor conductivity. Okay. They're not good at conducting electricity or heat. And because of that, they're poor conductors. So that makes them insulators, or maybe some are going to be better insulators than others. But great examples are things that are like petroleum based, like rubber, like, well, not rubber
Plastic.
necessarily, plastics, things of that sort. Yeah, those make great insulators because they don't conduct electricity. So this is one way we use molecular compounds. Covalently bonded compounds is as insulators. They also have low melting and boiling points. What was true about ionic compounds with their melting and boiling points?
They have ionic compounds have a high.
High.
Since they conduct since they have a lot of energy.
Yeah, so ionic compounds are bonded because one has stolen that electron. The bond is very, very strong. It's stronger. Ionic bonds are stronger than covalent bonds, if you want to think about it that way.
I have a question. So all ionic bonds are great conductors of electricity
In solution.
and covalent bonds are poor conductors.
Yes, but ionic compounds are only good conductors of electricity when in solution. Remember you tested that pile of salt,
Oh.
nothing happened. But when you put it in the water and the ions disassociated, then it was a great conductor of electricity. So when atoms share two groups of electrons, they form what kind of bond? Two groups. What do you think that would be?
A double bond.
A double bond if they share two groups. What if they share three groups?
Triple.
A triple bond. Okay. A molecular compound is a compound made up of what? What do you think?
Molecules.
There you go. Molecules is what we're looking for. So covalently bonded substances are molecular compounds. Ions create, which is a metal and a non-metal, you get your covalent or your, your ionic bonds. All right, so right here, it's comparing molecular and ionic compounds. And it's showing you right here, melting and boiling points for different substances. So here's your substance, your boiling point, your melting point, and it's showing you that which of these substances are your ionic compounds on this chart right here. Which ones, Eunice?
Calcium chloride and sodium chloride.
Yes, calcium chloride and sodium chloride are your ionic compounds. And then your covalently bonded compounds are isopropyl alcohol, octane, and water. Okay, so if you look here, here's your formula for each of these. Here's your melting point and your boiling point. Look at the melting point for your ionic compounds. How hot do you have to get before it melts?
75 Celsius.
That's pretty hot. And how hot do you have to get for it to boil? Real hot. Look at that. Look at that. Where does water's kind of where we base everything, right? Because we're a water planet. So melting point of water is 0 degrees Celsius. Boiling point of water is 100 degrees Celsius. And would you look at the difference between water and table salt, which is sodium chloride? All right, now today in lab, you're going to be comparing two very similar appearing compounds. You're going to have two white crystalline compounds. Okay, one will be sucrose, which is what?
Sugar.
Yep. C12H11O22. You had it.
C12H11O22.
Yeah, you had it a couple weeks ago or last week.
Last
week you had sucrose in lab, right? Okay, so you're going to have your sucrose, and then you're going to have sodium chloride, which is what?
Salt.
Table salt, okay? And you're going to be testing the bond strength by heating them. Yeah, and seeing what happens. All right, so melting points of molecular ionic compounds. All right, let me show you what's behind here. So that if you had filled this out, this is what you would see. Here's your melting points of these compounds. Here is, what's this one? Do we know what it is? It's right here, you see it? Isopropyl alcohol. I think that's what that one is. Yep, that's that one. And this one is octane right next, then water, and then calcium chloride and sodium chloride. So this is the difference between a table and a graph. Top is our table, and it's giving us the information in number and word format, so you can see it. The graph below it is giving you a visual representation of the difference. So you can see just how far it is from like the isopropyl alcohol at the front all the way to the sodium chloride on the other side. You can see how much space there is between them on a graph. So graphs are great for visual representation. So now I know that the properties of molecular compounds include what? What are our properties of molecular compounds? Eunice, what you got?
The properties of molecular compounds include high melting point, no, I mean molecular compounds, low melting points.
Low melting point, that's one. What's another one? Annabelle,
And, oh wait,
you have another one?
Ionic compounds have high melting.
Yeah, but we're looking at molecular compounds. They have low melting point, low what? If it's got a low melting point, it's likely got a low
conductor.
boiling point.
Boiling point.
And then how are they for conducting?
Poor conductor.
They're
So
poor, right? They're poor. So low melting point, inability to conduct electric current when melted or dissolved in water. Now, also I'll add covalent bonds tend to be able to stretch a little bit. They can stretch, they can go under some physical stress. Whereas, do you remember we said that ionic compounds are brittle? Like if you hit salt with a hammer, it's just gonna shatter, right? It'll make smaller cubes.
What about glass?
Glass is a little, so glass is made of primarily silica,
Oh.
which is formed like, it's volcanic. It's sand, right, basically. So, but we can change the way glass behaves based on, what we do with it. Do you need another pencil? Is it
Yeah,
not working?
the other one didn't work.
Yeah, I don't know what's up.
Thing kept.
Hang on, let me see if I have another one right over here, because people borrow them, but then they don't really borrow them, they just steal them because they don't return them, and then I run out. I have lots more upstairs, but here you go, this one should work.
I
Okay.
have no pencils too. It doesn't.
Here you go.
Right now.
Here. So, yeah, so.
Can I have another pencil too?
Yeah, that one didn't work. Okay. So, yeah, your covalent bonds can stretch some. And your ionic bonds, not so much. So this comes to like, yeah.
Thank you.
Remember when we talked, I think I mentioned it to you guys, or one of you guys, maybe you guys in the other class, but you can melt sugar and then pull it. You ever seen the candy makers that melt and pull sugar and it's really cool?
Yeah, like
That's because those because those covalent bonds can stretch. But can you do that with salt? No. All right. So now there are two types of covalent bonds. And so yes, you've got double, triple, single bonds. All right. But then there are two types within that. And they are non-polar and polar. Okay. Where is does Earth have poles?
Yeah.
Yeah, north and south, right? And they're magnetic, right? Does a magnet have poles?
Yeah.
A magnet has a north and a south pole, right?
And we need to stick a pole on the south and north pole, an actual pole.
That would be cool.
North and south attract.
Yes, north and south attract, opposites attract like repels. So you have polar bonds and non-polar bonds. And basically what that means is a covalent bond in which electrons are shared equally is non-polar. So H2 is a good example. See them right here? They're sharing it equally. Okay, but sometimes they're not shared equally. And when it's not shared equally, you get what's called a polar bond. That means one side is pulling that electron more, which means you have a slightly more negative charge towards whichever atom is pulling harder.
So is it an ionic bond?
Nope, these are all covalent bond. But you get a covalent bond. So your covalent bonds are subdivided into polar and non-polar. So it says round one, H2. So this one's a draw. The two hydrogen are pulling equally on the electrons. But what's happening here with the hydrogen fluoride?
The fluoride wants more.
Yeah, the fluoride wins. It has the stronger pull on the electrons, leaving the hydrogen with a slightly positive charge. And then that is how you get a polar bond. So covalent bonds in which electrons are shared equally is called what? What's it called, Eunice?
Are shared equally non-polar.
Non-polar. And what's it called when they're unequally shared? Everly? Polar, right. Okay. A great real life example of how this works. Water molecules are polar molecules, okay? And we take advantage of that all the time. Soap is a great example. Soap is a surfactant, and what it does is it's attracted to one end of an oil molecule. All right, so if you put oil and water and mix it together and you put soap in, the soap will like pull that oil away from the water, right? So surfactants are a way that we can take advantage of polar molecules.
Last class, before you said, guess the oldest thing in your room.
Oh yeah.
Is it the book under those pictures near the speaker?
Nope, it's not that. It's not actually in this room, but it's on this level of the house. You'll have to keep looking. What's the oldest thing? Because I have lots of antiques. So.
Is it the phone?
Oh no, way older than the phone. All right, so we'll keep guessing later, but let's get back to this. So your polar bonds. This talked a lot about polar bonds. It says water is an example of an ionic molecular compound. This type of bond forms when what? Does anybody have this answer?
What?
Right here. What type of bond forms when? So two nonmetals share electrons because it's a covalent bond, okay? It's a molecular bond. It's not ionic, it's molecular. We've circled molecular here. Properties of these compounds include, like we said, it's the same thing we said before, right? What is it, Annabelle?
Polar and
Low melting.
low melting point and low boiling.
Yeah, low melting, low boiling, and
Insulator.
poor conductors, right? Sodium chloride, what kind of a compound was this?
It's an ionic.
Ionic compound, and it forms when it's not two nonmetals sharing electrons. It's a metal and a non-metal with what?
With, it's a covalent, it's an ionic.
Yeah, it's ions, right? A positive and a negative ion come together. So it's a metal and a non-metal. Properties of these compounds include what?
High melting points, high boiling points, and great conductor.
Only when dissolved in solution, right? All right, so what type of bonds are formed when atoms share electrons unequally? Polar. And would carbon dioxide or water have a higher boiling point? Okay, Emerson, what'd you get? Water, why? There you go. So water, attractions between polar molecules require more energy to overcome than attractions between non-polar carbon dioxide molecules. How can bonding determine the properties of a substance? Ooh, what do you think, Eunice?
If it's an ionic bond, it's more likely to have high boiling and melting points.
Mhm.
It's an ionic bond, like it takes the electrons and it's like
Yeah, so in general, your ionic compounds have high melting points, conduct electric current when dissolved in water. Molecular compounds have low melting points and low boiling points and do not conduct electric current. Also, they can be a little stretchier, where ionic bonds are very brittle. So it says, now I know that some atoms in covalent bonds become slightly negative or slightly positive when what? What you got, Eunice?
when there are polar bonds.
Yeah, when they pull more or less strongly on a shared electron, which is a polar bond. Yep. Very good. So now let's talk about metals. All right. So it talks about superconductors. It says in 1911, physicist Heike Kamerlingh Onus made a remarkable discovery when he cooled mercury to negative 269 degrees Celsius, which is 4 Kelvin. That's real cold. I'd like to know exactly how he did that in 1911. The mercury no longer resisted the flow of electric current. The cooled mercury became the world's first superconductor. A superconductor is a metal that has no resistance to flow of electric current. Certain metals and alloys become superconductors as they are cooled to very low temperatures. This means they can carry electric currents for long periods of time without losing energy as heat. Superconductors can also be used to produce very powerful magnetic fields. These magnetic fields can be used to levitate and move high-speed trains. So, yeah. Yeah, so wait a minute, let me ask it. How is a superconductor different from a regular conductor? You answer this one, I'll let you do the next one, Emerson. What is it, Eunice?
A superconductor is a conductor that has no resistance and won't be transferred into heat.
Yeah, no energy transferred. They don't lose energy or lose very little energy.
Conductor, it conducts electrons.
Yeah, if you touch, sometimes you can touch certain wires, even if they're insulated, and you can feel the heat, right? Because you're losing energy as heat. All right, so Emerson, what about the next one? Power lines lose 10 to 15% of the electric current they carry to heat. Why might scientists want to create superconducting power lines? What'd you get? Yeah, and more efficiently, more effectively. That'll save money too, right? Because anytime you're losing energy as heat, that's money, right? Yes.
Okay, so I think this might be a around the point, but you said a superconductor is a metal, but the thing says material.
Yeah, but we're talking about metals because this is bonding in metals, this section, and superconductors are going to typically be specific metals. So, yeah. So what is a metal is a material. That's just another way to material's a broader term. So what is the structure of a metal crystal? Okay, metal crystal is composed of closely packed, positively charged metal ions. The valence electrons drift among the ions. So each metal is held in a crystal by a metallic bond, which is an attraction between positive metal ion and the electrons surrounding it. Okay, so in metals, you have what they call like an electron sea. So you've got all of these positively charged metal ions in tightly packed, and then the electrons are literally moving between all them. It's not like you have one, say you have one nickel atom, right? And its electrons are buzzing around it on the outside in the little electron cloud. Those same electrons don't stay with that nickel atom. They move between all the nickel atoms. So long as you're keeping the same amount of valence electrons, which is how it works, they're just going to kind of swap between them all. And because those negatively charged particles are in that sea and they're swimming basically amongst all those atoms, that's why they conduct electricity, because that electric charge can move freely from atom to atom because they're all mixed in together. So why would nonmetals be unlikely to have the type of bonding shown right here in this picture? What do you think?
Tightly, and because they hold their electrons tightly and don't lose them.
Yeah, because most nonmetals, they hang on to their valence electrons. They stay with that atom. But when metals are all bonded together, they don't stay with that atom. Those electrons move between all the atoms together. So metal crystals consist of what? They consist of closely packed, positively charged metal ions with valence electrons drifting among the ions. And they will call this, sometimes they'll call this an electron sea, like CEA, like the ocean, if that helps. So the attraction between a positive metal ion and the electrons surrounding it form what? What is this called? Do we know? Annabelle, do you know?
Sorry.
It's okay. Yeah.
Metallic bond.
There you go. Took a second, but you pulled it out of there. There you go. I was waiting patiently. It's coming. A metallic bond. Right. There you go. Okay. So look at this. What are the properties of metals? Well, check this out. Here is a motorcycle. So it's showing you lots of different properties. Metallic bonding explains the common physical properties of metals. Properties of metals include shiny luster, especially when polished, high levels of malleability, ductility, electrical conductivity, and thermal conductivity. The luster of a metal is due to its valence electrons. When light strikes the electrons, they absorb the light and then re-emit it. That's why it's shiny. That's why if you look at, like, this has some metal in it, all of those valence electrons are absorbing the light and re-emitting the light so that you can see the shiny appearance. Okay, so they are malleable, they have a shiny luster, and they're conductive. Metals act this way because the positive metal ions are attracted to the loose electrons all around them rather than to other metal ions. Metals conduct heat easily because the valence electrons within the metal are free to move. That's what we're talking about, the electron sea. So do you remember what malleable means? It's able to be what?
It can be hammered into things.
Hammered. What is ductile?
It can,
Wait a minute, Everly?
it can be pulled into a thin wire.
Into a wire. And what's luster, Emerson? It's shiny, right? And then they're conductive. All right, so it talks about conductivity on this page, and it says that metals conduct electric current easily because the valence electrons in a metal can move freely among all the atoms, which is what we've been saying. So here you've got luster, malleability, ductility, thermal, and electrical conductivity. All of these properties of metals exist because of how they bond to each other. Metal atoms bond to each other. So an example of a metal object that shows both luster and malleability. Who's got an example for me? Annabelle, what do you have?
A paper clip.
A paper clip, that's a good one.
Like that.
Yeah,
And
you got one?
maybe
The horn, the yellow thing.
Oh, the French horn?
Yeah.
Yeah. Anybody else have a different one? Aluminum foil, any of that. So gold, silver, jewelry, all of those things, right? So this talks about alloys. Okay, what's an alloy? What's an alloy, Annabelle?
A mixture made of two or more elements, at least one of which is a metal.
Yes. Can somebody give me an example of an alloy? What?
Gold.
Gold by itself is not an alloy, but typically the gold that you wear in jewelry does have some other metal added to it, usually nickel, because it provides strength. Gold is very soft. You know, those old prospectors, they would like bite their gold, right? To see if it was actually gold. You could actually dent it with your teeth.
And that's what the people are doing in the Olympics when they get.
Yeah, they're biting the metals, right? How about that chandelier in the dining room? Y'all have seen that chandelier, haven't you? It's dragons and it's made of brass. Brass is an alloy. Bronze is an alloy. Yeah, after class, you can go peek at it. So what accounts for the properties of metals? We talked about this. It's their loosely held valence electrons. Why are metals good conductors of electric current? Okay, who can summarize it? I've said it a couple times now. Who can give it back to me? Annabelle?
They, so metals are good conductors of electric currents because of their numbers of valence electrons and positively charged ions.
Yeah, there are a bunch of positively charged ions, and then you've got these valence electrons that move between all the atoms. You have that electron C, okay? That's what you need to know, that electron C. They move within the metal and they're free to like move all over the place. Okay, so how about, why is it safer to use a non-metal mixing spoon when cooking something on the stove? What do you think?
I think we could get a, why is it safe?
Like, why is it safer to use a wooden spoon than a metal spoon when you're stirring your pot of soup?
Metal spoon conducts electricity and it
Mhm.
might be a little dangerous.
Well, your stove doesn't usually put out electricity that's going to get you, but what does it put out? Heat. Anybody ever touched a metal spoon or a pot and been like, woo, shouldn't have touched that,
Yeah.
right? Way too hot. But wood isn't going to do that. So a non-metal spoon would not conduct the thermal energy, so it would avoid a burn. So now I know that the properties of metals include, we've done it a couple times, so we'll do them again. Shiny luster, high levels of malleability, ductility, electrical and thermal conductivity, right?
All the time.
All right. The what of a metal is due to its valence electrons absorbing and re-emitting light. What is it? What property is that?
Luster.
There you go. It's luster, right? What and what properties of a metal is due to how positive metal ion is attracted to loose electrons around it rather than the other metal ions surrounding it.
Malleability and ductility.
Malleability and ductility. There you go. Metals conduct what easily because valence electrons are free to move?
Heat.
Heat. And metals conduct what easily because valence electrons are free to move among atoms? Emerson. Electricity. There you go. Okay. Go. All right. So here are your answers. Let's have a look at these. Circle all of the covalent bonds in the dot diagrams. So you should have that. Those are your bonds. That's where they're coming together. So which bonds shown are double bonds? Eunice?
The oxygen.
And there you go. How about which ones are triple bonds? Which ones are triple bonds? Lucy, can you tell which ones are triple bonds? Number 3?
What?
It's when you have 3 pairs.
The nitrogen.
Yeah, girl, the nitrogen, real good. Okay, and which molecules have polar bonds? Can you tell? Emerson? Right. How can you tell? You see that little negative right there? That's telling you. So compare and contrast oxygen and fluorine. So what do we have? Basically, they're both nonpolar. Oxygen has a double bond and fluorine has a single bond. Okay, it says, I want you to notice, compare and contrast. Okay, when you get this question on a test, it's a 2-part answer. One part is how they're alike. The second part is how they're different. So if I tell you to compare and contrast something, your first answer should be to tell me how they're similar. In this case, they're both nonpolar. And how are they different? One has a single bond, one has a double bond, right? Some people will just compare or just contrast. Be sure that if you're ever asked on any test anywhere to compare and contrast, that you give both answers. All right, so what's number 6? Who's got number 6? Emerson. There you go. B, who's got number 7? Annabelle?
Double bond is a bond in which 4 electrons are shared.
There you go. Okay, E, very good. Who's got number 9? Eunice.
Non-polar bond.
There you go.
D,
And
D.
D, who's got number 9? Emerson. C, and who's got 10? Emerson. There you go. All right, so over here, what do points A, right here, and B represent? What do we have? Annabelle, what'd you get?
The positively charged ions and the valence electrons
Right.
are moving from that way to that way because there's a force moving.
So A represents your positively charged middle ion and B represents your free moving electron. What action is modeled in this diagram? What's going on here? Eunice, what is it?
Metallic bonding says the electrons are moving around freely and carry an electrical charge.
Yeah.
enabling the conduction of
But look right here. Do you see where that arrow is causing this to smush in and then this to poke out? This is showing you that this metal here that's being modeled is malleable. You see it? You see how all these guys are kind of displaced, but they'll bounce back, or they could bounce back. It depends. Depends on what you do, but you can keep smushing all the others around them. So how does metallic bonding explain this? What happened here? So basically, it's showing you that a force has moved some of the positive ions, but the attraction to the electrons keep the metal from breaking. That's malleability for you in a diagram. All right, what's number 4? Yes.
plus C.
See, what is number 5? Okay, go ahead, Eunice. D, let me give you the rest real quick. 6 is A, 7 is E, and 8 is B. So it says write a definition for these terms. A metallic bond is an attraction between a positive metal ion and the electrons surrounding it. And an alloy is a mixture of 2 or more elements, at least one of which is a metal. All right, I'm gonna skip this one, but I'm gonna put it in your notes, or I may come back to it at the end. So we'll go past it real quick. I wanted to show you this, and then I wanted to show you the give you your test prep stuff. So if you didn't know, over the weekend, SpaceX did something pretty amazing. So I wanted to show you in case you missed it.
The Stolen Valley.
And there's another commercial that I can't get rid of these. 2, 1, skip. There we go. Watch this.
What's going on?
Watch. Those are the chopsticks. That's right.
Oh, the people in space.
No, there weren't people.
We're back 7:30. Wow, I mean, that is a SpaceX Starship rocket booster for the first time ever. the booster returned back to the
The
launch
booster
site where it
was
was.
the top
And
in
cannibal
space.
chopstick, well, there were
Yep.
cannibal chopstick bombers actually, maneuvered the SpaceX fleet as critical to its goal of making that rocket fully reusable. That's impressive.
So in the past, they just had that rocket landing on the little landing pad out at sea, right? But now they've got it so that it's landing back at the tower with the chopsticks. Why do you think they're doing that? Why do they want it to land right back at the tower? Reuse it rapidly. They're talking like within a matter of hours. Yeah, they're real good. Okay, here are your Unit 4 test study topics. You have Unit 4 tonight. So, valence electrons and reactivity, Lewis dot symbols, covalent versus ionic bonds, characteristics of covalent and ionic bonds, naming compounds, writing formulas from compound names, polar covalent versus non-polar covalent bonds, cations versus anions, naming ions, naming ionic compounds, predicting the behavior, that should say of elements. No, predicting the behavior or elements of ions based on their location in the periodic table. And listen, for this test, a periodic table and a compound naming flowchart will be provided for you. So you will have the opportunity to reference that little flowchart that we saw last week. Remember where it's like, you name the metal first. Then you go and you look at
So
the.
you can use a periodic table like last unit test.
Yes, this one will be in, not with individual questions, but in the resources for the test. So you'll be able to use it whenever you need to. Yes.
The reason why I'm not wearing, the reason why I'm not wearing a denim jacket right now is because it's helping cover up my tablet and I don't want that to get stolen while my mom is walking.
Okay. All right. Well, I was going to show you that, but we don't have time. Be sure that you go back and look at this one in your note, in your resources, right?
What about the oil spill?
Oil spills. What about them? Where?
Oil spill.
I don't know. I'll have to look. All right. So get your lab ready.